everybody. Our next talk, I would like to welcome Michael Pegios to the stage. He's going to be talking about a talk that's entitled Going with the Flow, Apache Airflow for Operational Quality Scientific Workflows. He'll be joined by his colleague, Daehyok Shin, for questions, and they will share their experiences using Apache Airflow to build production scientific modeling workflows and give you all a few tips and tricks. Please welcome Michael to the stage.
Hi everyone. Unfortunately, our main presenter has called in sick today, so I'll just be doing more of a walkthrough of the slide deck. So this talk is going with the flow, Apache Airflow for operational quality scientific workflows. Starting at hydrological modeling and forecasting software at the Bureau. So primarily we use Python as our standard language using tools such as pandas and Xarray. We use Conda as our environment for managing and packaging these tools. A lot of our underlying tools and models are written in Fortran, C, and C++. We also have HP adjacent VMs that are running on multiple on-premises and cloud services. And we also have dev, test, prod environments for our research to operations team. Conda has been the standard environment management and packaging solution for several years. Also, we use pip packages as well. Many of our underlying tools and models are written in Fortran and C, but they either invoke either CLI calls or specific Python wrappers. So HP adjacent, that means we draw on outputs of the HPC models. We then need to do additional work to have some computing environments kind of set up on there. R&D tools development into workflows. So many tools have multiple use cases. We have a model development, which is an interactive use by hydrologists and transition to use in automated workflows. We also have scheduled operational workflows, which is the same operations at multiple locations. Retrieving, quality checking, and processing data, and running mathematical models, post-processing, and product generation. So all of the pain points noted above are especially issues with planning handover to ops teams. Many of our Python apps are written with multiple use cases in mind, automated using workflows plus interactivity for hydrologists, I think Jupyter notebooks. This is the main concept of our talk is Apache Airflow. So Apache Airflow is now a mature open source platform to programmatically author, monitor, and schedule workflows. The core concept in Airflow is called Directed Acyclic Graph, or DAGs. They're a pipeline of tasks with a set of dependencies that you chain on together. These DAGs are then defined programmatically through Python, so it's kind of essentially a workflows code platform. Relationships between these tasks are defined using special overloaded operators. Unlike other systems in Airflow, there's multiple ways to do this. So you can use classes, decorators, context managers. These are kind of how you define your DAGs. That overloaded operator is a right shift operator. So that's how you kind of, a special character that you use to kind of define the task dependencies between tasks. So you just write an arrow. It looks very simple and easy to use when you're writing Python code. You also have an Airflow scheduler, so that kind of sits in the background. It reads and loads in the DAG definitions, and it can distribute the tasks to the workers to actually do the computations themselves. It comes with a full-featured web GUI for monitoring, for scheduling the DAG workflows. So if you need to do some error monitoring and see the status of your DAGs, you can use that full-featured web GUI for that. Our two use cases for using Airflow, one that's already completed is called eReefs, G2G or grid-to-grid system. That was a project to develop operational ready capability for water runoff to the Great Barrier Reef region to our external partner agencies. And then we also have SSF, Seamless Technology Integration, or the SETI project that's currently in flight. So that's the transformation of our internal existing Bureau services, including greater automation and more frequent delivery. I'll go over now through the eReefs project. So this is something that we were involved in last year. It's a multi-agency project that provides monitoring and monitoring of the Great Barrier Reef, or the GBR region. The initiative of eReefs is to track and predict the condition of the reef. So we want to see, kind of where the health of the reef is currently at and predict what will likely happen in the future so we can see how healthy it is and make informed decisions. Our involvement in eReefs was to deploy a large-scale grid-to-grid water quantity model for the Great Barrier Reef to AWS. This includes water quality post-processing outputs. The water quality post-processing would provide constituent concentrations for the previous 24 hours using the grid-to-grid outputs as an input. Grid-to-grid itself is a hydrological model designed by the UK Centre of Ecology and Hydrology. It kind of simulates the stream flow across the surface by driving land surface area into grids and then using these as predictors for water flow between these cells. To deploy this model, we developed a workflow in Airflow to deliver data daily to our customers in near real time. Going over some of the challenges that we faced with eReefs. So how do we sync all our data, tools, and software from our internal Bureau system to AWS? How do we access and modify the data on AWS using Airflow as well? So thinking about storage options, what can Airflow actually use on AWS? And thinking about how we can actually modify the data. We also want to create a redeployable system that we can transfer to partner agencies. So one of the goals with the project was to create a lift and shift system. We create a workflow tool that we can provide to our partner agency, CSRO, where they can actually take over the operational system and be able to run it for themselves without our reliance on being able to set up the workflow for them every time. And also developing a solution given time constraints. So we had about 6 months to develop this whole eReefs deployment. We also had new developers on board, so that brought in another challenge of how do we get new developers on a new tool working very quickly, which leads on to the reason why we selected Airflow in the first place. We did a workflow assessment. We have some internal workflow engines, and we found that Airflow, since it's just written in Python, if you can read and write in Python, you can write a workflow in Airflow. It's very simple and easy to use. We also had data sharing was one thing. So we wanted to share data to our partner agencies, to CSIRO, to the Australian Institute of Marine Science and the Queensland government. They were all using AWS as a solution. So it just made sense to select AWS to be able to share that data around. Cloud first and cloud right. So these are kind of Australian public service initiatives where we kind of choose cloud as the first technical solution if we can. So since AWS is on the cloud, we were able to choose that. And then open source. So we wanted to share our code. We wanted to get greater collaboration between other developers. AWS, Airflow, and Python is just a larger community. And I feel like we just were able to get better contributions when we're going to open source. So that leads to managed workflow for Apache Airflow. So Moi is the Airflow service that AWS provides. It allows you to have the Airflow service without you manually configuring the infrastructure itself. So AWS will manage all those services for you. This was our starting point. This is what we started off. We had a single DAG and we had a single package. Corello, which is the Python tool that does the data preparation. We have the DAG itself, which defines the workflow. We just manually copied these up to our EC2 instance using our AWS CLI, using the CP command. We had our Elastic file system that mounted onto that EC2. We then create our Airflow environment through Conda, which then calls the Python operator. So whatever the Conda environment that you created Airflow in is what's going to call the Python code. So whatever that Conda environment you set up initially. This is based on a DAG schedule, so it's kind of like a cron tab if you're familiar with Linux. Basically, you set up a schedule for how often this DAG runs. And this is where we landed at. So this is kind of the final deployed system. We have more DAGs, more packages, going over to more automation as well. So we were able to think of more storage and infrastructure set up for our eReef system. So we were able to launch our infrastructure. We leveraged Terraform, which is an infrastructure as code tool, to create and provision all these resources. You can see we have more now. We have ECR and ECS for containerization. And we have S3 and EFS for our storage option. That gets all wrapped up in a VPC, which Terraform just creates automatically for you. So that fulfills our requirement for being able to lift and shift this operational system. We also have GitHub pipelines through GitHub Actions that creates these CI/CD pipelines to push our DAGs onto an S3 bucket. So we have our data preparation DAG, our G2G DAG, which is the model itself, water quality post-processing, and the data fulfillment, which then sends that data out to our external agencies. The MOA then picks up these DAGs from our S3 bucket. Automatically, you do not have to fiddle with it. As long as the DAG is in there, it will just automatically pick it up, and then it will just run it. We also have our packages, Corallo, G2G wrapper, Corallo water quality, and eReefs preparator, which all correspond to a single DAG. We can push and board our images from those packages onto AWS directly. So we can push that container image into ECR, and then we can update and deploy the task definition into ECS. Once we have our containers, we can then call our ECS operator that runs our container image as a task within our DAG, and that runs on Fargate, which is a serverless compute engine that just then uses the EFS that we have defined in the ECS, which then we can share our data to partner agencies through S3. And this is kind of the overall deployed system. It kind of hides away all that complexity we saw in the previous slide. It's a very simple Web2 UI. It's consistent and clear, and it allows staff who are non-technical to be able to delve deep into what ran and what didn't run and be able to retry tasks. Moving on to the SETI project. So the foundations of the current SSF service, developed as a service during the Millennium Drought, launched in 2009. We use statistical model BGP or Bayesian joint probability distribution, which is forecast range of likely outcomes. There's 300 plus forecast locations across Australia, and the BJP is based on this long-term kind of stored data record using other inputs. The key data flows here, we have our ORL model running on our Bureau HPC on the left. We apply some spatial and temporal processing with some streamflow observations, which then get put into our staging database. These then get calibrated BJP models, which allow us to have forecast streamflows across those locations and then create forecast products. So you can see on the bottom right, we have the forecast products there. While you could run one of these as a single DAG, splitting it into multiple ones helps us with the condo environment management. It also helps separation of concerns and different support teams for when the system is operational. Key concept is task parallelization and data grouping. So the goal is to use underlying grouping of data for load balancing tasks, then organize them into task groups. So here we have our custom grouping function. Let's just define there. We call it at the startup during the DAG definition. It's just a single Python file where we call that grouping function as part of the configuration. They passed as arguments to operators and tasks in the next slide. Oh, sorry, I omitted the next slide because it's too detail-oriented. So task parallelization, small sample result. For simple scenario of the previous slide, data ingestion, we have 40 forecast locations that are split into 4 groups. We use our Airflow's local executor, which is the same VM process-based, and we reduce the runtime from 3.8 minutes to 1.5 minutes, which is 42% of the original runtime. Our simple workflow distribution algorithm is a limiting factor, which can be easily improved. We'll get improved performance for larger volume of work. Airflow has multiple worker backends, but in our experience, at least local executor is not suited to very fine-grained work parallelization. Our Airflow scheduler and workers handle details of task multiprocessing, including configurable handling of failures, monitoring, and GUI. Some of these conclusions are our use case reflections. We have easy to set up Airflow cost, but there's also flexibility in the programmatic DAG, so it's kind of workflow as code, like I mentioned before. For eReefs, it was feasible to onboard new developers mid-project and be productive at the same time. They were able to get up and running quickly with the DAGs because they were able to read and write in Python. Bridging the scientific research and development with operations, we were able to iteratively develop workflows, kind of utilizing that CI/CD mentality. We can deliver consolidated system to ops with web UI for monitoring, and there's scope for further improvement as required with more frequent releases. Further work and improvements, better integration with Conda environments. There's this new thing called Conda operators. So actually, instead of using the Python operator that just runs that Conda environment that Airflow was set up in, you can use a Conda environment to actually call a Conda environment that you have. Improve our DevOps for dev to production deployment. So we kind of have a clear separation of development and production. Previously, we'll just work on that single Airflow environment, but having separation clear of concern will make sure that we can test our changes before we deploy them. Integrating Airflow error reporting into the Bureau's enterprise incident management system, and building a new system with Airflow with more modular design and smaller micro apps. Thank you for your time.